Have you ever wondered, if a black hole can capture even light, does its gravitational influence propagate faster than the speed of light? If black holes are truly faster than light, wouldn't that imply the existence of faster-than-light phenomena within the universe? The mere emergence of this concept is chilling, as it directly challenges our most fundamental understanding of the cosmos. The speed of light is the absolute cosmic speed limit, an ironclad law inscribed into the foundation of physics by Einstein himself. Should a black hole violate this fundamental law, the entire framework of the theory of relativity would collapse.
Our comprehensive understanding of space-time, causality, and reality would instantaneously disintegrate. However, the underlying truth is profoundly more severe than this conjecture. A black hole's gravity does not propagate faster than the speed of light. Rather, its mechanism for capturing light is far more bizarre and absolute than sheer velocity. Furthermore, the phenomena in the universe that genuinely appear to exceed the speed of light are in fact far more daunting and bleak than black holes. First, let us examine the precise mechanism by which a black hole captures light. A black hole is not a colossal cosmic vacuum indiscriminately drawing matter in. Rather, it is a region of extreme space-time curvature. When a stellar body exceeding 3 solar masses exhausts its nuclear fuel, its core collapses under its own gravitational influence to such an extreme that its entire mass is compressed into a mathematical singularity. This singularity possesses a volume approaching zero and density approaching infinity, warping the surrounding spacetime akin to a profoundly stretched rubber membrane. The closer one approaches the singularity, the more severe and steep this curvature becomes.
A photon invariably travels at approximately 300,000 kilometers per second. It neither decelerates nor ceases its kinematic motion. However, in the vicinity of a black hole, its trajectory is so intensely curved that it points exclusively toward the center. Visualize standing on the edge of a phenomenally steep funnel, attempting desperately to escape outward. Regardless of the direction you step, the surface beneath you inevitably directs you to the bottom. Light experiences the exact same phenomenon. It is not being pulled backward. Rather, all of its possible linear trajectories have been warped into inescapable topological dead ends by spacetime. It continues to propagate at the speed of light, yet all forward paths converge on a single destination, the event horizon. The event horizon acts as the unidirectional membrane of the black hole, with a radius defined as the Schwarzschild radius. For a black hole of 1 solar mass, this radius is approximately 3 kilometers. For a supermassive black hole of 1 billion solar masses, it can extend to tens of billions of kilometers. Once any entity traverses this invisible boundary, even light is compelled to move exclusively inward, precluding any possibility of escape. Observed from the exterior, it would manifest as a dark sphere emitting a faint red glow.
This occurs because light, in its final moments of attempted escape, undergoes severe gravitational redshift, appearing exceedingly dim and red, akin to a dying ember. From the interior perspective, the very concept of an exterior ceases to exist. Spatial and temporal coordinates become fundamentally inverted. The forward direction points inevitably toward the singularity, rendering even spatial retreat impossible. A prevalent misconception asserts that a black hole possesses infinite gravity, thus allowing it to surpass the speed of light. At a distance, a black hole's gravitational field mirrors that of an ordinary stellar body, adhering strictly to Newton's law of universal gravitation. Only upon close approach to the event horizon does the space-time curvature become exceptionally extreme. This phenomenon is not dictated by the propagation speed of gravity, but rather by the geometry of space-time. Einstein's general theory of relativity articulated this principle with absolute clarity over a century ago. Gravity is not a conventional force, but rather the geometric curvature of spacetime. A black hole simply warps this geometry so profoundly that all potential exit trajectories for light are completely sealed.
What then is the propagation speed of gravity? The formulation of this question actually harbors a slight misconception.
The mechanism enabling a black hole to capture light relies on static space-time curvature, rather than gravity traveling at an extraordinary velocity. A static gravitational field is not a signal continuously emitted from a black hole. It is the intrinsic geometric topography of space-time itself, existing simultaneously throughout space. A photon perpetually travels at the speed of light. It is merely that all its potential linear forward trajectories have been curved into dead ends, eternally directed toward the black hole's singularity.
Conversely, rapid dynamic changes in the gravitational field, such as the coalescence of two black holes, propagate outward as gravitational waves. On August 17, 2017, humanity achieved the first simultaneous detection of both gravitational waves and electromagnetic signals. This was the GW170817 event, generated by the inspiral and merger of a binary neutron star system. The gravitational waves and accompanying gamma-ray burst reached Earth nearly contemporaneously, exhibiting a time differential of less than 1.7 seconds. This observation provided direct empirical proof that dynamic changes in the gravitational field propagate precisely at the speed of light.
Consequently, the gravitational behavior of black holes is in absolute accordance with general relativity, displaying no evidence whatsoever of superluminal propagation. On September 14, 2015, LIGO achieved the first direct detection of gravitational waves, originating from the merger of a binary black hole system. The signal emanated from a distance of 1.3 billion light-years, involving two black holes with masses of 36 and 29 solar masses, respectively. During their final orbital inspirals, they revolved at near-light speeds, ultimately coalescing into a single remnant black hole of 63 solar masses. The total energy dissipated during this event was equivalent to 3 solar masses being instantaneously converted into gravitational waves.
Yet, upon the arrival of these gravitational waves at Earth, their propagation velocity remained strictly the speed of light, devoid of any superluminal characteristics. Therefore, a black hole's capture of light is not predicated on superior velocity, but rather on profound topological alteration of spatial pathways. It warps spacetime into an irreversible unidirectional manifold. Light continues at the speed of light, yet it remains perpetually confined within this curvature. This raises the question, do any genuinely superluminal phenomena exist within the universe? Affirmative, and it is profoundly more extreme and bleak than the physics of black holes.
It is the cosmic expansion of the universe itself. In 1929, Edwin Hubble discovered that the vast majority of galaxies are receding from our observation point. Furthermore, their recession velocity is directly proportional to their distance. Contemporary astrophysics confirms that certain galaxies near the edge of the observable universe are receding at superluminal velocities. While this superficially appears to violate the theory of relativity, it fundamentally does not.
Special relativity exclusively constrains an object's local kinematic motion through space to subluminal velocities. Cosmic expansion, however, involves the metric expansion of space itself. Galaxies are not propelling through space, but rather the interstitial spatial fabric between them is continuously stretching. Consider an inflating balloon with ants drawn on its surface. As inflation progresses, the proper distance between the ants increases. The ants undergo no local locomotion. Only the underlying two-dimensional space is expanding. Given a sufficient rate of expansion, the relative recession velocity between two distant ants can easily exceed light speed, despite their local crawling remaining strictly subluminal. Currently, the co-moving radius of the observable universe is approximately 46 billion light-years, whereas the universe's chronological age is merely 13.8 billion years. The reason this radius vastly exceeds the product of the universe's age and the speed of light is precisely due to spatial metric expansion. During the transit of photons from those extremely distant galaxies, the intervening space expanded significantly. Consequently, the photons we currently observe originated from coordinates that were substantially closer at the time of emission. More disconcertingly, this expansion is undergoing acceleration. Dark energy is driving space to expand at an ever-increasing rate.
According to recent data from the Planck satellite and the DESI experiment, the acceleration parameter of cosmic expansion is evolving.
In several tens of billions of years, all galaxies beyond the local group will recede at superluminal velocities, rendering their emitted photons permanently incapable of reaching Earth. We will progressively lose causal contact with the remainder of the cosmos. The entirety of our observable universe will be reduced solely to the local group, floating like an isolated island within an increasingly void and expanding darkness. In approximately 1 trillion years, even the neighboring Andromeda galaxy will redshift beyond the cosmic event horizon.
Ultimately, our perceived universe will consist exclusively of the Milky Way and its bound satellite galaxies. All other structures will transition into eternally unobservable darkness. This represents genuine superluminal recession, not a physical object in kinematic motion, but the spatial fabric itself tearing apart. Whereas a black hole locally induces extreme space-time curvature, cosmic expansion universally stretches the space-time metric. The former confines light within a localized gravitational cage. The latter continuously expands the cosmic cage until photons can never traverse the expanding gap. Therefore, when inquiring whether black hole gravity exceeds the speed of light, the rigorous scientific truth is far more unyielding than mere velocity.
Black holes curve the local trajectory into oblivion, while universal expansion severs the global trajectory entirely. Both phenomena articulate the identical fundamental truth through distinct mechanisms. The speed of light serves as the ultimate causal constraint, the final safety lock of the cosmos. Once this threshold is surpassed, whether through localized extreme curvature or global metric expansion, we irreversibly lose contact with the external universe. We exist within a universe that is inexorably expanding and stretching its own fabric. The speed of light represents the ultimate cosmic limit. Black holes weaponize this limit into an inescapable cage, while dark energy weaponizes it into an eternal severing of causal ties.
And humanity currently exists in the transient epoch between these two extremes, shining briefly, persistently, and with profound defiance. Black holes do not propagate gravity faster than light, and cosmic expansion does not induce true superluminal physical motion. Concurrently, they demonstrate that the cosmos is fundamentally more exotic, severe, and elegantly complex than we historically conceived. And we are momentarily situated precisely at the intersection of this magnificent cruelty and profound beauty.